All right, this is Physics 1C for May 4th, and today we're going to be talking about mostly Faraday's law and this concept of what's called electromagnetic induction. Electromagnetic induction is the way in which a moving magnetic field can produce electric currents in wires, and it is the kind of force that powers all of the electrical power production in the world. Is this idea of EM induction. So we'll learn what that is today. And we're also going to start off by talking about Ampere's law, because there's one type of problem we haven't done, and I know for a fact that it shows up on your next lab manual assignment, which is due, in like 3 or 4 weeks or something like that. So let's do it. That's this problem right here. Okay, so let's have a review of what Ampere's law is, because it's been like 5 days. So Ampere's law was a thing where we basically took a line integral around a closed path of a magnetic field, and we found that it would be equal to mu naught times the current that was kind of enclosed by the path, or that penetrated the path, the surface bound by the path. So that's what it is. And really what this allows us to do is it allows us to find the value of what the magnetic field is. That's usually what we use it for, because the current is usually known, mu naught is a constant, and the path is a choice. So the only thing that's really an unknown is B. So we use this to find magnetic field. So here's an example of a magnetic field that we can, or of a type of wire that we could find a magnetic field for. So it says a cylindrical conductor with radius capital R carries a current I. The current is uniformly distributed over the cross-sectional area of the conductor. Find the magnetic field as a function of the distance r from the conductor axis for both points inside and outside of the conductor. Okay, so luckily they've drawn the whole picture here, so let's just look at the picture and take some time to understand what's happening. So the cylinder here, which is gold, is kind of a metal that has current flowing through it, I, in this direction. And we want to find the magnetic field both inside and outside. And so 2 different paths have been drawn here with, I'll give a name to this right here. I don't think I used this name last time. We call these loops like Amperian loops. I don't know when that language came around, but nowadays that's what we call them. This is similar to when we did Gauss's law, we had Gaussian surfaces. So for Ampere's law, you have Amperian loops. And really what it is just, it's a loop that's drawn in space around which you're going to do this line integral. This path integral, and yeah, you just want to choose it in such a way that it makes the integral easy to do, just like with Gauss's law. So let's look at the one inside. This is the one that's actually more interesting. Okay, I don't know how well you can tell this, but there are 2 different radii and 2 different circles drawn here. So capital R is the radius out to the edge of the cylinder, and little r, which is less than r, is the radius of this blue loop right here that's going around in a circle like this. Okay. Now, if you were to use your right-hand rule and you point your thumb in the direction that the current is flowing, is it properly? I don't know. So the current's kind of coming out towards me this way, which I guess, I don't know how to draw that so that you guys can see it. If you point your thumb in the direction the current's flowing, then your fingers will wrap around in the direction that the loop is drawn. The loop is drawn that way, so around like this. That means that when I draw the dl portion of this, so let's draw one vector for that. If I were to draw it right here where B is, it would point exactly in the same direction. That's the way dl would point. Up over here, it would point kind of up this way. It's always going to be tangent to the path, which means that B and dl are pointing in the same direction, so we can change this integral to just being the integral of BDL is equal to mu naught times I enclosed. Now we can start thinking about what the current enclosed is going to be. The current I is the total current that flows through this system. So when I have a loop that has a radius little r that is smaller, here I wrote over the part that has, so the radius is r. Since that loop is smaller than the radius of the wire, that's going to change how much current is actually enclosed by the loop. Does that make sense to you all?
Yeah.
Okay.
Yeah.
So how do we kind of determine how much current is actually in there?
Ratio of areas.
We can do that. That will definitely work because we know that the area of the larger. Oops. So one thing we could do is we could just take the total current and then multiply by the ratio of the areas, the cross-sectional areas, which would be pi r squared divided by pi times big R squared, right? And this would be equal to the current enclosed. Okay, so that's one way we could do it, and that's certainly what we'll do for this problem, I guess. That's the simplest way to do it. But we'll do another version of this problem right after we do this to show you what would happen if the current I was not constant. Okay, so current enclosed is going to be I times pi r squared. We don't need to write the pi again, right? It's just going to be little r squared divided by big R squared. Okay, and then over here, we can pull the magnetic field out, and the integral of just dl is going to be 2 pi r, which is the path length. And now we're pretty much done. We just need to divide all this stuff to the right-hand side. So we end up getting that the magnetic field inside, so this is for the region where r is less than big R, the magnetic field inside is going to be equal to mu naught I. We'll have a single r. I'm going to leave that out to the front, divided by 2 pi big R squared, and yeah, one of these r's cancels. This one cancels with this one. Yeah, and then times r. So a bunch of constants multiplied by r, which means that, you know, if we were to plot this, the magnetic field as a function of the radius basically just goes like this. Just a normal kind of straight line slope where the slope is given by that piece right there. So that would be the magnetic field inside the conductor. Without actually going through the steps, I'm just going to go ahead and say that for r greater than big R, the answer that you're going to get is that B is going to be equal to mu naught times I just divided by 2 pi r. This is the same result that you get if you have the magnetic field of a wire that you don't worry about the thickness, basically. So we've already done this. And again, you can go through the same calculation. The only difference is going to be this piece right here, where this is just going to be I. So this term isn't here, so that you can see pretty simply that you're going to get the exact same answers I have here. And if we plot that one, it's going to kind of fall off like this, right? So that would be your total magnetic field as a function of radius, where this little branch point right here, the place where they change, is capital R. And of course, you can plug big R into either one of these equations, and you'll get the same equation. If you plug in big R for little r, they match at the boundary. Okay. So that's what you do if the current is uniform, but it doesn't have to be uniform. So for example, what we could do is we can say, suppose instead of being told that the current is constant here, say instead that you're given that the current density, so J stands for current density, okay? I'll just remind you because we don't use this very often. This is current density, which basically is just current divided by area, right? That's all it really is, current divided by cross-sectional area. So the current density in this wire would be I divided by pi times R squared, right? So, but suppose that the current density J, instead of being just I over A, what if it was given as K times R squared? Okay, so some constant multiplied by R squared is what our current density is going to be. So then what you have to do is you have to kind of rewrite what Ampere's law is. So now what you can do is you can say, if that's what the current density is, and what this really means is that, you know, when R is equal to 0, the current density is 0, but as the R increases, when you get to the outer edges, the current's getting more and more dense, right? If you wanted to kind of draw that, I don't know if this would be useful, but what that would look like is, suppose you use little dots to represent the current density. The idea would be that when you get to the outside right here, the current is really dense. There's a lot of current, basically. But when you're on the inside here, the current is kind of more spaced out. And yeah, it just is like as you go farther out, you just have more current, basically. So it's a little sparser in here, and then it gets more dense as you get to the outside here. If this is our cross-section of the wire. All right, so if you do that, then what you have to do is you have to say the current enclosed now is going to be equal to an integral, and this is going to be, I guess this is a surface integral, ugh, I hate saying that, but I think it is a surface. It's definitely a double integral of, and now it's going to be of j dA. Kind of like flux, because it's a surface integral. Do you still call that a surface integral? Is that what that's called?
I think so.
I mean, the A, I think the way this would look in your math textbooks, I think often they put ds, right? With S representing surface, is that right?
Yes.
Yeah, okay. So I think it's the same thing. In physics, we just always use A. I don't know why. I don't know why. I don't know why we haven't, after all these years, found a way to get our math textbooks and our physics textbooks to kind of be really similar to each other in terms of the way we do things. I mean, they're not. It's not like they're completely different languages, but it's kind of like different dialects or something like that. You know, where it's the same language, but sometimes you might not recognize the way it's written or the way it sounds. Just like you could go to the deep, deep South and you could talk to someone from Alabama and you might not understand anything they're saying, even though they're speaking English, supposedly. So yeah, I don't know. It's weird. Anyway, so if we use this as our definition of the current enclosed, and this is our current density right here. Okay, let's just redo the problem, and let's find the magnetic field again. Okay, so exactly same problem, but we want to find the magnetic field if this is the value of the current density, and let's also say that this is the current density just for r less than r, because that's going to be the edge of where the conductor is. Okay. All right. So then what we have to do, the left-hand side of our equation is going to stay the same. So I'm just going to leave that as the same. It's going to be b times 2 pi r. Nothing's going to change. The right-hand side of the equation now is going to be mu naught times this integral. So this is going to be the integral of j dA. Now j is going to point in the same direction as the current. So for example, if these dots represented the direction the current's flowing, the area vector points in the same direction. We'll call this dA. So j and dA are parallel to each other. I meant to pick this one, but didn't do it. So j and dA are parallel to each other, which means that when we do the integral, this will just become j dA. And I'm going to skip another step. I'm just going to go ahead and plug in j here. So this is going to become k times r squared times dA. Now for dA is basically going to be the area of a kind of donut that you draw inside of this, okay? So the way we would do this, so this is our big R, right? And here's our little r. And what we do is we draw a ring right here. And then say that this ring that we draw has a thickness, dr. Okay, so it's really going to be like two concentric rings. It's going to be like a ring like this and a ring like this. And the thickness is going to be dr. And the radius is going to be r. I don't know how well I can draw this on here, but yeah, imagine a ring right here. And then the area of that thing is going to be dA. And the area of that thing is going to be the circumference, which is 2 pi r times dr. Okay. Does that all seem familiar to you all? Does that make sense?
Yeah.
Okay. Okay. And then we just do the integral, right? I mean, at this point, from here, it's pretty easy. So you've seen stuff like this before, right? We're just applying the same kind of we're just solving the surface integral. Yeah. Okay, so we can't just cancel these 2 pi r's out. That's something I would have done when I was in high school. Like, oh, 2 pi r, 2 pi r. Can't do that because it's inside the integral. There's a dr right here, so we have to actually evaluate the integral. This constant k is just some constant that I made up, so we can pull that one out. So k times mu naught. We can also pull out the 2 pi's. And we're left with just this integral. Technically, since I've gotten rid of this is only a single integral now. So now we just have, what, r cubed dr? We evaluate that. Oh, and we need to go all the way from zero to r. Not big R, though. We're going to go from 0 to r prime. We basically want to integrate out to the radius, basically like out to this radius right here, basically. Okay. So we'll call that r prime. It's the same r as this one, but we just don't want to use the same variable. Okay. And then I think we can evaluate this. So we end up getting K mu naught. This 2 pi will cancel with the 2 pi that's on the other side. So we'll have B. We can divide by R for this R. And this is obviously going to be what? R to the 4th over 4. From R prime to 0, which is just... The R prime is a dummy variable, so we just make it R again. So we end up getting B is equal to K mu naught R cubed divided by 4. I think that's right. Did you all see any mistakes that I made there? Or are there any questions about some of the steps that I made? What is clotted cream, by the way? Do I want to know what that is? Is that like another name for cottage cheese or something?
You know, it's like a... I mean, I saw it being... Well, I didn't see it with my own eyes, but they, like, leave, like, thick milk out, and the next day it accumulates a bunch of fat on top, and then they just scrape the fat off and eat it.
It sounds like cottage cheese. Or something. I don't know. Maybe I'm wrong. Okay, so... any questions about this, how to do this? So I know you have a problem like this, so that's why I brought it up, and your book doesn't really describe how to do this, so... There you go. That means that there is kind of a better version of Ampere's law, where you basically write it like... you write it like that. So we'll need this version of Ampere's law later on too. And this still isn't the complete version of Ampere's law, because there's also going to be a plus another term here that we don't know how to talk about yet, but we will after this chapter. So I think that's it. That's kind of the end of Ampere's law. And actually, we're not going to talk about this today. We will later. The next topic is electromagnetic induction. And really, I think the best way to begin with this is what I would do if we were in like an actual laboratory, is I'm just going to show you one of these simulations of how this works, so that we can then kind of talk about what's happening. So we don't need any of these. I always have to turn these on. Okay, so there it is right there. Now, we've already seen something that kind of, and we've already talked a lot about this kind of stuff. So now we're just gonna actually put the math behind what we've discussed. Okay, it looks like it's showing. The right stuff here. Okay, so electromagnetic induction is the idea that if I have a magnet, right, we know that magnets produce magnetic fields. Magnetic fields look like this thing here with all these little compass lines. And, yep. So right here we have, this is just called, it says pickup coil, right? So what we have is basically a light bulb. The light bulb is connected to some wires. So this is just one continuous wire that comes in this side of the light bulb here. And then if you follow the wire, it goes around in a loop like this. And then it loops around one more time. And it goes back into here. I believe we can control the number of loops. We can go down to 2 or 1 or 3. Not a lot of control, but we'll start with just 1. We can also change the loop area. We can make it bigger. We can make it smaller. And we can change the magnetic field strength. Let's go ahead and make magnetic field strength at maximum. And then, oh, so we can either, yeah, I think we want to use this one. we'll start with a light bulb, and then we'll go to this one so we can understand what's happening. Okay, so this is what electromagnetic induction is. If I have a coil of wire, so to be clear, there's no power source within this right here. Okay, now, obviously, this is a computer and it's a simulation, so you have to just take my word for it that this works. But the idea is that there is no battery, okay? There's no battery, there's no power generator, this light bulb's not hooked into the wall. I mean, it's turned off, right? That makes sense. But if you take a magnet and you move it near this, like this, coming kind of in and out of the loop, you'll notice that the light bulb lights up. Now, it doesn't light up when you just put the magnet inside of it. It only lights up when you move the magnet near the object. Okay? And you can see that that moving the magnet around right here, it heavily alters the magnetic field in this region, right? You can very easily see that by moving the magnet around, the magnetic field gets altered. Now, nothing really happens if I move it like this, although it kind of does. Maybe a little bit. I guess if I go fast enough, something will happen. But it's when you move it into the actual loop itself that you get major amounts of... You can really see the difference, right? When I go up and down here, it does look like the light bulb is lighting up, but when you push this inside like this, even when I do it very, very slowly, you can see that the light bulb's lighting up. Now, there are flashlights that work off of this principle. Have any of you ever heard of like a Faraday flashlight? A Faraday flashlight is a flashlight where it doesn't have a battery, and the way it lights up is you basically you shake the flashlight, and it has a magnet inside of it, and the magnet basically does this. And then it also has some capacitors to kind of store some residual charge so that it'll stay lit. Have any of you ever seen this before?
Yeah, I've had one before.
Okay. So yeah, magnets moving near loops of wire produce electricity. That's how this works. Now we can say even more about it if we put a voltage meter on here. Now the voltage meter allows us to see the direction of the current. Now you could actually see, I don't know, did you notice what was happening with the direction of the current in the wires right here? Can you see what's happening? Can anyone describe physically what's happening there as I move it in and out with those electrons?
Or just begin to move.
Can you say more about it?
They seem to alternate.
Yeah, they alternate, right? So they go one way when we go this way, and then they go another way when we go the other way. In fact, let's see, is it the same way? So when I push this in, they're kind of going downwards, and then when I pull it out, they're going upwards. So you can see four different things here. First of all, when I push the north end in, they kind of come down this way. When I pull the north end out, they go back up the other way, right? Now what about the south end? If I push the south end in, they kind of come down this way, and I pull the south end out, they go back up the other way, okay? Now it's even easier to see, I think, if we put the voltmeter on here, because this will give us a voltage that's either being positive or negative, right? Come in, it went negative, pull out, it went positive. You see that? Negative, positive, negative, positive. So we're gonna learn why it goes this way. Now another thing we can do is we can increase the number of loops here, and it should make this effect even bigger, right? You can see that even with moving this very slowly, that the voltage is deflecting much harder with 3 loops. And if I go quickly, you can see that the voltage will go very far. So you can start to kind of write down what are the things that actually affect this, What are the things that actually are happening here if I wanted to kind of come up with a way to describe what's happening, what matters. We can see that number of loops matter. The size of the magnetic field matters. Like I can make the magnetic field much weaker, and the effect would be much weaker. So the size of the magnetic field matters. The number of loops matter. The loop area also matters. If I make the loop area smaller or bigger, how did that affect it? Maybe that one's not so obvious. Let's go to the extremes. So this is a 20% loop area, right? With 3 loops. I move this in at a certain speed. I move it out at a certain speed. It's maybe going to about a little under half of the meter reading, right? It really depends. I can make it max out by just going really fast, by the way. So I have to be really kind of careful about this. So I'll just kind of gradually pull this in and out. If I make the loop area bigger, you all tell me what you think happens here. Does it seem like
Voltage.
Much more drastic.
Yep.
Yeah, it feels more drastic. Now, again, I can't prove that I'm not just I can't control how fast I'm moving this in and out, right? I wonder if any of these has something where we can consistently move the magnet, you know? Oh, this one actually does in a weird way. Okay. Okay, yeah. So this is the other portion of this. I remember the first time I saw this like live when someone demonstrated this, and I was just utterly shocked. For some reason, for me, when I look at what's happening here, this is pretty impressive. I mean, this is really crazy. The fact that you can just move a magnet and it can make currents move, like that, it can make electrons move in a wire. That's really surprising, you know? But maybe it's not that surprising, right? Because what have we learned that allows this to be possible, like in this class? What allows this to work like this? That moving the magnet will make the charges move. Have we learned anything that makes that seem physically reasonable?
I mean, there's like a field, there's a magnetic force that acts on charges.
Yeah, we already know that magnets affect charges. We also know that when a magnet is at rest near a charge, what effect does that have on the charge?
No effect.
No effect. The charge has to be moving, right? Or the magnet needs to be moving relative to the charge or something. You'd have some kind of relative motion, or else you're not going to get any. So yeah. So it's probably not, I don't know. Is it surprising to you seeing this? Like, you see the magnet goes in, you see the, is that surprising to you? I mean, it's kind of impressive, right? I don't know if it's very surprising or not.
There's like no contact force necessary to cause the charges to begin to move.
Yeah, exactly. That's true.
Oh, wait. So, I mean, velocities are relative in the real world. So,
Sure.
does the force equation kind of like have inconsistencies with like who's measuring which velocity?
No. I mean, like, let's say that you can look at this from two perspectives, right? Like, magnet can move, something happens. Or the coil can move, and still something happens, right?
Mm-hmm.
So it doesn't matter if I live in a world where I say the magnet is moving, and you live in a world where you say that that this thing's moving. It doesn't matter. You both are going to agree that there's a voltage, right? Now, that being said, there is more to the story, which we're going to get to later on, because we can maybe talk about it today. I don't know. There is a, I don't know if paradox is the right word, but there is something that, like, depending on your motion relative to an experiment, it might change how you observe a field. Like, you might be moving relative to an object and think that there's an electric field there, but somebody else might be sitting still and they might think that there's a magnetic field there. So let's talk about that later on after we get through this topic, because it's definitely something we want to talk about at some point in this class. There's actually a discussion of this at the end of the Physics 1C lab manual that I can point to, which is before the problems. But this is one of the problems that Einstein took up when he was looking at relativity. So relativity has the answer. So there is a problem, Cam, that we'll talk about later, and relativity solves the problem. Okay, so so maybe this isn't too surprising. For me, for some reason, though, this one is kind of surprising. So here we have a basically an electromagnet, right? 10 volts, you've got currents flowing through here, so we know that there's a magnetic field that points through here. And if we wrap our fingers in the direction of the current, which is opposite the direction of the electrons, there's a magnetic field that points this way. And you can see the magnetic field lines. You can also see that they're pretty much the same as the magnetic field lines of a dipole. And so, of course, if I take this loop that has its own magnetic field, then I can also produce the exact same effects that I did before, right? Because now I can just move the coil, which is an electromagnet, in and out of here. And I'll also produce this, right? And again, we can make the loop area bigger. Now let's switch over to this, and let's see that we can also alter the magnetic field here by just controlling this voltage, right? Like if I drop the voltage to 0, there's obviously nothing happening. But if I go from 0 to something, then you see a change, right? And if I go from 10 to negative 10, you also see a change. If I go from negative 10 to positive 10, you see a change. Do you notice that it goes the opposite way too? This is one of the things we're going to learn how to do today. Watch what happens when I go from 10 down to negative 10. It goes positive, right? And if I go from negative 10 to positive 10, it flips negative. And that's really because if you look at what these compass needles are doing, all you're really doing is changing the polarity of your magnet, right? This is like taking a magnet and just flipping it back and forth, right? Boop, 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 boop. And by doing that, you produce a current in this wire. In fact, the type of current you would produce in this wire would be what we call alternating current. Alternating current is current that does not flow in the same direction all the time. You know, so sometimes it goes this way, then that way, then this way, that way, that way. Okay, so that's like alternating current. Now here's the thing. You've certainly heard of direct current and alternating current. We've talked about direct current in this class. But even before you took this class, you had heard of DC and AC. Would you all agree?
Yep.
Yes.
Okay, all right. And so, I don't know if you had this question, but you may have had a question like, what's the point of even having direct current versus alternating current? Like, isn't one of them just better than the other one? You know, why would we ever use maybe you thought, why would we ever have alternating current? Seems like direct current's really good. Well, this is one of the really strong advantages of alternating current. With direct current, there is no induced EMF here. We call it induced EMF, by the way. Sorry, I'm using that phrase. But when you have this electromagnetic induction, okay, so we call the EMFs that are induced EMFs. Okay, so when I move the magnet near the coil and I produce a voltage, we call that an induced EMF. So we're inducing an EMF in this coil by moving the magnet. Okay. So coming back to this piece right here, when you have just direct current flowing here, there is no induced EMF, right? The wire that doesn't have a battery, the one that just has a resistor and a voltmeter, there's no current flowing, right? But if I make it so that the current over here automatically goes this way, then that way, then this way, then that way, you do induce the EMF here, right? And if you do it in a constant way, which is what AC is, so now we have an AC current supply, okay? And you don't see it moving much, but this needle is going back and forth and back and forth. So there's an induced EMF, but that induced EMF is constant, basically, right? Not constant, but it's continually happening. Put the light bulb on here, we can see that the light bulb would basically just stay bright. Yeah. Now, let's put more loops in there, because that should make this effect bigger. Kind of did. It's hard to see, though. Can we get more loops? No more than 4. So all we can really do now, if we want to make this effect bigger, is just flat out increase the amount of voltage we have right here. Now, there's 2 different knobs here. I'm pretty sure this knob is going to increase the peak-to-peak amplitude. So that should increase the voltage here, which I think should increase the wobbliness of this needle. Let's see. So I'm going to go up a little bit on this. Let's see if it increases it. Would you agree that it's kind of going left and right more now, even though it's not very much?
I see it.
Okay, and so let's just go up to maximum so we can get the biggest effect possible. Okay, so this just means all that I've changed here is like if before it was 5 volts positive and 5 volts negative, it's now 10 to negative 10. Okay, so there we go. Now this knob here, what do you guess that this one's gonna modify? If this one modified the amplitude of the wave, which is the peak-to-peak voltage, this is voltage, by the way.
Gotta be frequency.
It's probably gonna be frequency. Okay. Now, do you think that modifying the frequency will have an effect on what's happening here?
Will it make it like wiggle back faster?
Okay, that's reasonable. It almost has to, right? It has to wiggle back faster because if you look at the frequency on the left and the frequency on the right, they're pretty synced up, right? They almost have to have the same frequency, right? It's hard to tell because the loops on the left are so big or so small. But if I make these loops smaller, you can probably see it a little better. Not really. Okay. So I guess my question to you is, do you think that you all agree that the rate at which this thing is going to wobble back and forth is going to increase if I increase the frequency? I guess the question is, do you think the amplitude at which it's going back and forth will get bigger, or do you think it'll stay the same?
I would suspect this.
Okay. I'm just going to ask the question again to make sure everyone understood the question. So, first of all, we said this knob on the bottom is going to change the frequency, and I wanted you all to predict like what's going to happen. And the first thing people said was, well, this is going to oscillate back and forth faster. So the second question is there going to be an effect on the amplitude of the swings? Like, is it possible that I increase the frequency and it starts to swing all the way out to here and here, or even just a little bit more? So what do you all think?
I think it'll stay the same.
I think it'll stay the same. Okay. What does everybody else think?
I suspect the same too.
Okay. Does everyone at least understand the question? Does anyone want to ask a question about like what I'm asking?
So we're changing the speed that's oscillating, right? We're not changing the actual strength of anything.
Right. Yeah. We've already maxed out the strength, exactly. Okay, let's see what happens. So I'd say right now it's hitting, I wish we had numbers, but it's kind of nice not having numbers because we live in this digital world. It's almost barely hitting about halfway to this pixel right here, right? To that first mark. And not quite making it.
Yeah.
Yeah, okay. So let's just see. Let's go all the way up. Maybe I'm crazy, but it looks like it's going about twice as far now. Am I wrong? We'll go back down again. This was 50%, so half the frequency. So notice that the arrow, basically, the edge of the arrow here, the edge of the arrow barely touches that first tick mark, right? And when we go to 100%, the arrow very clearly makes it farther, in my opinion. Not a lot farther, but it's definitely farther. Would you all agree?
Yeah.
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 Okay. So that to me is really surprising. It's not just how strong the current is that affects it. I mean, obviously, if we make the current really weak over here, voltage is super low on this side. That's going to have an effect. That's not surprising at all. But the frequency literally looks like it has, like, when we doubled the frequency, it looks like it doubled the amplitude here, right?
That is surprising.
Yeah. So that actually tells you something about what's happening, right? So I think we now have, most of the pieces that we need to talk about how electromagnetic induction works. So it appears that it depends on, first of all, the magnet has to move, or the magnetic field has to change in some way, right? And it looks like the rate at which the magnetic field changes has an effect on how much EMF you get, basically, right? It appears that when the magnetic field's changing very quickly, that the induced EMF is even bigger, okay? So that should maybe start to get you thinking about what it's going to be related to, right? And maybe that makes you think about, it's a rate, right? Frequency is a rate, the rate at which these things are moving back and forth. So if the rate at which they're moving back and forth affects the overall amplitude, then that's kind of a hint that this has to have something to do with derivatives. You know what I mean? Because when the rate gets bigger and it affects how big this is, would you all agree that has to have something to do with derivatives?
Mm-hmm.
Okay.
Yeah.
Okay. So what else is there to say? The only other thing I'd want to do here is show you what happens. You can kind of do it with this one, but not really well. What I'd love to be able to do is I'd love to be able to kind of alternate what's happening here. And instead of like going back to the pickup coil example here, all we can really do in this example is do this basically, right? The one thing I'd like to be able to do would be able to take the magnet and just rotate it in a circle, or to take the coil, right, and rotate it in a circle, like basically flip it on its end. But we can't do that with this. The generator kind of allows us to do that, though. So I feel like we've looked at this before. Maybe I'm wrong. But let's crank up the strength again. Let's get the loops up. Let's get the maximum effect we possibly can here. There we go. And yeah, and then we'll just turn this water on. So this is basically what a hydroelectric dam does, if you think about it at the end of the day. So a hydroelectric dam is something in which you dam up a river, and you basically control when water flows from the high side of the dam to the low side of the dam. And when the water's flowing, like it is here, water flowing down. You have the water flow over something like a turbine or whatever. This is like a water wheel, right? But then the water wheel itself is attached to a magnet, and then that magnet is nearby some kind of a pickup coil like this, and you can see that that rotating magnet has the exact same effect, right? Has the exact same effect that we saw when we were just moving a magnet back and forth, right? So you don't have to have the magnet just go straight in and out. That's what I'm trying to emphasize. It's really any motion of the magnet near the coil is going to induce an EMF in the coil. Okay. Notice what happens too. If you were to describe the type of current that's flowing through this coil on the right, how would you describe it? Is it direct current or is it alternating current?
Alternating?
Alternating.
Yeah. So now there's two strong reasons why alternating current's good, right? One reason is because in the case of the transformer, which we're going to talk about what a transformer is later, but not important. This is basically a transformer. If you have alternating current on the left, you automatically induce EMF on the right? So that's one advantage of alternating current. And then when you look at the generator, you realize that, well, what's a generator? A generator is something that takes mechanical motion and turns it into electricity, right? So it looks like this generator, which is one of the simplest types of generators that you could probably construct, it naturally produces alternating current, So if this is going to produce alternating current, then what's the point of turning it into direct current? It turns out there's not much of a point, because when you want to send current over long distances, you can do so with alternating current much more easily. And by more easily, I mean more cost efficiently. I think, and this is something where I've read about this, but it's been a long time, so one of the early kind of struggles with electric power production in the United States was that Thomas Edison wanted to use direct current and Nikola Tesla wanted to use alternating current for power transmission. And one of the drawbacks to using direct current was that you had to have power stations dotted throughout the city, almost similar to the way we have how cell phone towers are kind of just everywhere these days. You need to have a lot of them if you want to get.
Mm-hmm.
So that's what Edison's DC power supplies power plants would have been like. There would have been power plants for every single neighborhood would have its own power plant basically. But with alternating current, it turns out that you can actually just produce all the power at one location. A really extreme example is the Hoover Dam, which is in southern Nevada. How far away is the Hoover Dam from us? A 5-hour drive, probably, something like that.
Yeah.
Maybe more. It's pretty far, right? But the power that's produced with the Hoover Dam is actually used all over Southern California, in San Diego, LA. You know what I mean? Because we can transport that power at a very, very low current. And then we can use this device right here, which is called a transformer. You've all heard of transformers, right?
Yeah.
And these are the things that they're on top of telephone poles. Sometimes during the summertime when it gets really hot, they pop and burst, and they have to be replaced, right? Well, this is basically what a transformer is, okay? It takes current flowing in one wire and gets it flowing in another wire. And it turns out that the number of turns in one wire and the number of turns in the other wire have the ability to basically take the current, if it comes in at really low current, but high voltage, you can basically make it high current and low voltage. So what that means is that basically the current that's coming in over the power lines could be maybe 10,000 volts or something like that. And then when it gets to your transformer, it gets stepped down to 110 volts, which is what you use in your house, right? And the advantage of that is you send the current over long distances at a very low current level to cut down on losses due to friction, basically. Losses due to interactions with the material of the wire. So, anyway, yeah. I'm sure I missed some of the details of that, and if you want to read more about it, you certainly are welcome to. Maybe you can tell me some things I don't know about it, but that's at least a couple reasons why we use alternating current today. And we're going to spend a whole chapter on looking at circuits that have alternating current sources, because they're a little bit different from DC sources. And we've only been talking about DC sources up till now, and now that we've introduced electromagnetic induction, we can really explore that. So now this is kind of an introduction to the rest of the course, right? for the rest of the course, this is kind of what we're going to be talking about, is trying to understand this connection between electricity and magnetism through this phenomenon called electromagnetic induction, and this will really be the main topic for the rest of the semester. It's just kind of understanding this phenomenon, mathematically talking about how it works through Faraday's law, and then looking at what kind of things you can do inside of a circuit with it, by placing coils inside of circuits to kind of hold energy in forms of magnetic fields. Okay. But we can kind of ahead of ourselves. We want to actually mathematically describe what induction is, so let's do that. Let me just look at the time real quick. Okay, we'll probably go for another 10 minutes, then we'll take a break. So, electromagnetic induction. Okay. So as we saw, the idea is take a coil of wire, take a magnet with a north end and a south end, move the magnet near the coil, and you will get what's called an induced EMF in the wire. So an induced EMF is an induced EMF that is an EMF that's produced inside of a wire due to a magnet being moved near it. Okay, so the first thing to describe then is under what circumstances are you actually going to get an induced EMF? Okay. Okay, so there's different possibilities for when an EMF can be induced in a coil. 1, the magnetic fields can change in some way. Not can, is. That's what I want to say. So in some way the magnetic field needs to be changed. It can be done so by motion, like we can move the magnet around. You can rotate the magnet, or it can be done by a change in current in the case of an electromagnet, which is what we said with this piece right here. Okay, to go back to the DC thing. No induced EMF over here, but if we alter the current in some way, now we actually can induce an EMF, because we're basically flipping the magnetic field inside of here, right? And again, this is a change in the magnetic field, right? Even though the magnetic field shape is the same, right? If you look at the red and whites, the reds and whites are flipping, right? Red becomes white, white becomes red every time we do this. So that is a change in the magnetic field. Okay. So some way the magnetic field needs to be changed, okay? Other things that can change it, or other things that can affect it, the area of the loop can change. This is something I didn't show, but we can... Okay, again, I need to be careful about the language I'm using here. This should be the area of the loop is changed. So let's see, I actually didn't show that one. Let's see if we can prove that that one's true here. So let's go back to our pickup coil. I wonder if this magnetic field's too uniform to make this work. I don't think it is. It should work. Okay, so let's look at our voltage right here. And all I'm going to do now is I'm just going to shrink the area and see if you see a voltage change here. It did, right? You can barely see it, but it's happening, right? If I do it slowly, you're not going to see it, but if I do it really fast... Oops, if I don't take my cursor off the screen. Can you see it moving? You know, it might be easier with the light bulb, actually, because then we don't have to... Yeah, there we go. Can you see that?
Yeah, much clearer now.
Yeah.
Yes.
Because Because it's just a super small effect. I wonder if we applied that same idea to our transformer, because we were trying to figure out what happens with the frequency, right? I wonder if I changed the light bulb, if you can see the effect. So that's 50% light bulb frequency. And if we double the frequency, yeah, you can tell, right?
Yeah.
The little lines are getting longer. Okay. All right. So going back to what we were trying to prove, though, it does seem to be the case that just by altering the size of the loop itself, just by doing that. Now, what does that make you think about? Why would that matter? Why would the size of the loop matter? Why would that matter? Any ideas?
I mean, there's more material in the loops. More loop.
There's more stuff, for sure.
And more charge able to flow through it.
What's physically changing? Like, think about the things that we've...
The density. The flux.
The flux, what do you mean?
Are you talking about like
The
amount of
magnetic field flux.
Yeah,
Yeah,
the
I think
flux
that's
is
true.
changing. Exactly. Okay, so when the area changes, since flux is magnetic field times area, B times A, B is staying the same, but A is going up, right? So the flux is changing. Exactly. Okay, so now we're getting to the kind of meat of what we want to do. So again, what are we talking about here? We're talking about induced EMF, which is the EMF that happens when you move the magnet near the coil, and I'm saying that you can induce such an EMF when the magnetic field is changed, or when the area of the loop is changed, or, and the final piece is the angle is changed. So area of the loop was A, basically. And the other possibility is that the angle between B and A is changed. Those are the three different things that can induce an EMF in a wire. Either the field is changed by motion or by some change in current in the case of electromagnet, the area of the loop is changed, or the angle between B and A is changed. And so now, especially after what Cam had already said, it should be pretty obvious that when you put all these things together, you could summarize all of that by saying what changes. What one thing contains magnetic field, area, and the angle between the field and the area.
The magnetic
The
flux.
flux, right? So really it's the flux, magnetic flux, which, to remind you what it is it's basically, the integral of B dot dA, right? So when flux changes, you get induced EMF. And this is what we call Faraday's law. A change in flux produces an induced EMF. And we can write that in an equation by saying that induced EMF is going to be equal to, there's going to be a negative sign here. We'll talk about why that's the case. This is actually a pretty simple equation. It's just the derivative. You take the derivative with respect to time of magnetic flux, and that gives you the actual value of the induced EMF. There's no constants, which is actually kind of amazing. Almost all of our equations in electricity and magnetism have some kind of a constant that shows up, Right? Like there's Ampere's law, there's the mu naught that shows up, right? But even the definition of flux, there's no constants. It's just induced EMF is equal to the time rate of change of the magnetic flux. And there's a negative sign here for a reason that we'll discuss, but it's mostly due to conservation of energy, or something called Lenz's law. And the other piece of this is the number of the loops actually matter. So also on this, you also put in front of here N, where n is going to represent the number of loops of wire. There we go. That's Faraday's law. So you can either think about it like this. When flux changes, you get induced EMF, or you can think about it like this. But either way, this is Faraday's law. I don't think Faraday would have ever written it down like this, though. Just from what I remember from reading Faraday. Faraday was a very experimental person. Like, he would have thought about it more as, like, these three things are how you induce EMF. And he played with different wires and shapes and found ways to maximize it and stuff like that. But this is our modern version of Faraday's law. And it's really simple. It just says that when you have a change in flux, it's going to induce an EMF. And this idea is, you know, one of the kind of applications of this. There's a lot of applications, but, you know, one of the applications is generators. Wireless charging. Anyone here have a phone that has a wireless charger? Like those little things you plug into the wall, and it's like a little circle, and to charge your phone, you just put your phone on the circle.
Yeah, I have one of those.
You have one of those? Okay. So that works off of Faraday's law. It works off of electromagnetic induction. You can have current go from one object, the charger, into your phone without the need of wires, basically, right? That's pretty powerful. There's tons of other, there's a lot of other applications of this. Transformers are another application of Faraday's law. Maybe you all can think of some applications of it. So, anyway, we'll spend the rest of today's class exploring problems that we can solve with this, and just talking in general about it. Anyone have any comments or questions?
I was thinking, do you know, or anyone like know how like good those wireless chargers are? Are they just something like cool to look at, or do they actually like, is it like a viable kind of cost-effective charging method?
They work, but you also have expensive phones that you want to put a case on, right? So at the same time, it would be kind of annoying to take your case off to charge it and then put it back on every other day.
Do you have
So
do you have to take the case off to charge it?
It depends on how nice of a case you have. Like if you have because usually if you want to have like some kind of like thicker case to protect your expensive technology, you don't want. It depends on your phone, but like I have an iPhone 12 and I can do it with it, but the simple core is just very convenient and fast. So
Exactly. It's also nice to not have holes in your phone, right? Because if you have like, and they basically tried to get rid of this stuff completely. I mean, I have a Motorola or something, so it still has the headphone jack, but I think iPhones don't have headphone jacks, right?
Nope.
Nope.
Do they still have? The? If you have the wireless charger, does it still have the port, like the USB port?
It has like lightning cable, yes.
Okay, so the lightning cable's still okay. I would suspect that they want to get rid of that too, though, right? Because
Yeah, to push everyone towards wireless charging.
yeah,
Mm-hmm.
because then you don't have any possibility of like foreign substances getting into your phone, right? Like sand, and dirt, and oil, and whatever that can get into those little holes and then can, cause problems. But
Yeah.
now another question you asked is it power efficient, Cam?
Mm-hmm.
I would say, okay, my guess is number one, probably not. It's probably more power efficient to just plug it in. The other thing I would guess, though, is that it kind of is probably negligible in terms of your power usage for your home,
Okay.
Because if you actually calculate how much it costs to, like, charge your phone, it's going to be like a penny or less, probably. Maybe a little bit more, I don't know. And if you calculate, like, on your electricity bill, basically, like, it's not really going to be a big portion of your electricity bill is what I would guess. So, yeah. Also, like, there's other things that use wireless charging other than just phones. So I have an electric toothbrush, and yeah, that uses wireless charging. There's just like a little dock that you put it into, but the dock doesn't have any like electrical connections on it. It's just like plastic on plastic, and it works off of same concept, electromagnetic induction, to wirelessly charge the toothbrush. So, yep, and that's definitely a place where, because it's a toothbrush and toothbrushes get wet, you wouldn't want to have electrical contacts on the outside of the toothbrush, right? Because if you did, then they would be exposed to water, and they would rust, and they would corrode, and then the contact wouldn't be as good anymore. Because as soon as you have rust on a piece of metal and you try to connect it up to something to charge it, then if there's too much rust, it won't make an electrical contact, right? And as a result, you won't get any electricity. So, yeah, there's a lot of other applications of wireless charging other than just cell phones. I think the cell phone wireless charging thing is newer, though, right? It's like in the last 10 years or so that's become a more common thing to see. Oh, and one of the I think what I think is like one of the most interesting. Okay, we really should stop. But we'll keep going for just a moment because we stopped her a little late. Yeah, okay, I'll just put it like this: induction stoves. Has anyone ever used one of those? An induction stove or an induction hot plate?
Used them in the past, yeah.
So the way these things work, this is really interesting, is you need to have. So okay, so here's your
Like huge resistance.
It just needs to be made out of a magnetic material.
Oh,
So,
okay.
so an induction stove, the way that it works is it's gonna look like your basic like hot plate kind of thing. In fact, if you've ever been to someone's home where they have like their stove is like just this big piece of plastic, and the burners are like underneath it or whatever, or maybe it's made of glass or something like that. It might be an induction stove. Doesn't necessarily have to be though. So the interesting thing about induction stoves is they work off of this principle here, and so the way it works is you have your vessel that you're going to cook in, right? So you've got your pot right here, and let's make it somewhat circular so it looks like a pot. So here's your cooking pot, and the pot needs to be made out of like iron, for example. It's like iron or some kind of magnetic material, I think is what I want to say. I may be wrong about that. I think it can't be ceramic. It might just be that it needs to be metal, honestly. This part I might be wrong about, okay? But if it's something like iron or some kind of magnetic material, the effect is going to be even crazier. And so then what you have down here is you have an induction coil, which is literally just some kind of thing that has current flowing through it, and it alternates the current back and forth and back and forth and back and forth with the goal of producing induction. So how does it produce induction if you just have this this pot right here? Well, it produces little tiny currents inside of it. Okay, so you'll have these little tiny currents that get produced inside of the material here, basically little loops of currents and stuff like that, right? And then because the induction coil is like oscillating back and forth in terms of its current, then the currents also oscillate back and forth. And so that as you have the currents like oscillate, what you're really doing through this induction coil down here is you're making the electrons inside of the material basically just go back and forth and back and forth and back and forth. And so then through the effect of resistance, the pot basically heats up.
Is this supposed to like evenly cook the food too?
It has a few different effects. So one effect is that, yes. Why would that be? Do you tell me? Why would that be the case? Why would such a pot like this
I was
more
imagining
evenly
because of
cook
the
compared to fine?
oscillations, right? Like the
Okay.
currents continue to oscillate, so it's like it's a constant.
Yeah, when you say
It goes
constant,
back and forth. Like,
Say-
constant as in like, not like. I'm not sure if like the magnitude of the current is gonna be the same, but like it's continuous, you know? It keeps going back and forth.
okay. So let's compare it to a gas stove. Like what is the actual difference here? So let's put our same pot on a gas stove. Now, the difference is I can put a ceramic pot. Ceramic pots are really nice.
Oh, I see.
What's the difference between the type of
It's
heat?
like hot spots.
There's hot spots, exactly. All of the heat in a gas stove goes into the bottom, okay? All of it goes into the bottom.
Which is
So,
why you have to like mix the food.
Yes, exactly. So if you're cooking like a sauce or whatever, and you just throw all the vegetables and your meat and everything in the thing, you can't just let them sit there. You're gonna have to mix them around because otherwise the stuff on the bottom is gonna get burned. And so you need to keep kind of making it flow around. You don't really. I mean, you're still gonna have to mix things with a system like this. You wouldn't want everything just stuck on the bottom, but the bottom is no hotter than the top, and the entire vessel that you're cooking in gets the same temperature basically. So the food basically gets cooked on all sides, which is nice, really uniform cooking. The other thing that's interesting is if you take this thing off of the stove, you can actually touch the coil, and it won't be hot. The coil is it's going to be underneath some plastic or some whatever, but you could literally take the pot off, and you have to give it a little bit of time because the lower surface is going to get hot because the pot itself is hot. But if the induction coil was on its highest possible setting, you could totally put your hand on top of it and you wouldn't feel anything. Why is that? Why could I put my hand on there and I wouldn't feel anything, but if I put the pot on there, it would get hot?
Your skin's not like made out of.
It's not a conductor, your hand.
Yeah, your hand's on a conductor.
It's not as good of a conductor.
Yeah, exactly. It does conduct electricity, it just doesn't do it as well. So you're not going to get these huge these currents inside of here, right? So that's a type of induction heating. This is extremely popular in China, I want to say, and in Europe. And it is slowly becoming more popular in the United States in newer homes that people will put these in. But you can go buy, I'm not saying you should, you can go buy a hot plate that works off of induction heating. And it's kind of cool. I would like to have one of these. I would love to know what the difference would be, if you could even tell the difference between cooking food in one of these versus cooking food on a gas stove. Chances are you probably couldn't tell a huge difference. One thing, though, that I did notice, I was watching a YouTube video where someone actually did an experiment where they tried to see which one of these would boil water faster, and the induction coil was faster because, again, the whole thing is getting heated, so it's going to be quicker at like transferring heat into the water that's inside of it. So I think that the one on the right's faster at boiling water than the one on the left. Also, because it uses induction as opposed to gas, gas stoves are nice, but like they require burning things, which is, it means that the grills get a little bit dirtier. You have to clean it more frequently. You have to relight the pilot light. You need to make sure you have a store of gas, whereas electricity is a little easier to get to. Okay, so people are typing things in chat, and I'm not looking at it. Okay, Prince Ali says he uses one. Oh, you're talking about the wireless charging. Yeah. You all use cases on your phone, huh? I had a case on my phone for a while, and I just got tired of it and took it off.
Honestly, I should probably get a wireless charger. Like the little end that you stick into the phone.
Yeah.
Like it gets bended for me sometimes.
Yep.
So the charging just gets weaker. So yeah, I might buy a new one.
Exactly.
Or a wireless charger.
Yeah, exactly. When you have parts that touch each other, they inevitably will wear down over time. Yeah. Okay.
I wonder if it's less material. It takes less.
What, the wireless charger?
Yeah, I'm looking at my wire. I'm like, okay, so there's definitely copper and other metals in here, alloys.
Mm-hmm.
So like, how much does it take to actually make one of those things? Maybe
The charger or the phone?
the charger.
Mm-hmm. I'm pretty sure I can say, without a doubt, the wireless chargers are larger. So they must take more material, right?
Oh, they're bigger. Okay.
Yeah, because it's like a little, you plug it into the wall and then it's like a little circular pad, right? Is that right? I don't have one, so I don't know. I just have seen commercials and I've seen people using them in coffee shops and stuff. Sometimes that's the other thing about it, is that you can have, there are many types, Ali says. there are lots of different types.
Different colors, different flavors.
Yeah. You have one with a stand. Nice. It is kind of nice, like, just the idea of being able to have, like, a surface on which you could just put a bunch of phones and they would all charge, right? Like, that is a lot better than some of the setups that I've seen in people's homes where, you've got an outlet and it has, like, 6 different outlets, and out of those are multiple extension cords that people have, like, 4 different, iPads and iPhones and, gaming devices that are all plugged in. That's not very feasible, right? I mean, it's also not very safe to have a bunch of things plugged into one outlet. But if you just have like, imagine that someone sold a coffee table that also acted as a wireless charger, where like as long as your phone was on the table, it was charging. Like that's pretty. I don't know. That's a pretty handy thing to have.
There's this really cool version they had. Like, if you attach it to, I think it was like a ceiling light of sorts. You had to do this whole fancy installation process where you can wirelessly charge everything in the room.
Really?
Yeah.
That's really cool. See, there you go. Now that's what I'm talking about.
5G. The 5G.
The only caveat was that you have to have like a sort of adapter, but those adapters are pretty easy to get.
Okay.
So like you just plug into your phone and it just automatically charge everything up, no
See,
matter where you are in the room.
See, that's amazing. So now what you're talking about is some of like the real like ways in which it could improve our lives. Which, one of the biggest problems with cell phones is they just go dead a lot, right? And the longer you use it, the battery gets worse. And with a lot of modern cell phones, they don't want you replacing the battery, so you basically have to get a new phone. But if we had ambient wireless charging going on in our homes, and you literally never had to charge your phone, I mean, that's a huge quality of life adjustment, right? Like, what if you just never had to plug your laptop in, right? What if you never had to plug your phone in? It was you just had your laptop, and it didn't even have wires. It just was, you just took it wherever you went. Same thing with your iPad. Like, that is amazing. And I think that's, maybe I'm crazy, but like that's certainly kind of the direction things will probably be headed, because we always try to make technology more and more usable. And this is the piece of this that I find crazy. The technology for this has existed since 1850s, right? I mean, this is old. Like, Faraday lived in the 1850s. Like, this is very, very old concept. But it's only recently that we started to see commercial applications of these type of things. And I remember when I was in college, like when I first learned about this is, that's the kind of stuff I was talking to my friends about at the time. It's like, wouldn't it be cool if our laptops and our wireless mouses and stuff, if we never had to charge them? And we're kind of getting to the point where that's definitely the case. Do I know of any side effects of having a battery underneath you basically driving? No, I don't think there shouldn't be any side effects of that. No, I think that's safe. I don't know. Maybe I'm wrong, but the battery shouldn't do too much to a human.
Do I want Bill Gates reading my brain though?
Reading your brain? How would he read your brain? What do you mean?
I don't know.
5G.
Not 5G.
Oh, is that what 5G does? It's like mind control technology. Mm-hmm.
Exactly. Gotta wear those tinfoil hats now.
Yeah, definitely. Don't ever take off the tinfoil hats. Okay, let's take a break. We'll take a longer break because we're almost to like 30-minute mark.